Good evening, one and all. Welcome to the Kaapi with Curiosity talk. Very happy to see you all here. Now I request our director, Dr. Guru Prasad, to formally welcome the gathering.
Respected speaker of today's Kaapi with Curiosity lecture, Professor Sukanta Bose, other academicians and professors, ladies and gentlemen, and my colleagues from JNP. I welcome all of you heartily to this yet another lecture in the Kaapi with Curiosity series, which is jointly hosted by International Center for Theoretical Sciences, ICTS, and Jawaharlal Nehru Planetarium, and hosted here every month. It's one of the most popular and lecture series and well-received series. And today we have a special topic. Anyway, you can see I don't want to preempt neutron stars, natural laboratories for universes, smallest and largest scales. As the honorable speaker has said, he's going to link what is at the elementary particle level with the structure of the cosmos, physics of the very small with the structure of the cosmos. So I don't want to preempt more. And once again, I welcome you all to this Kaapi with Curiosity lecture. Thank you very much. And Sharanya, take over, please.
Now I call upon Dr. Prayush from ICTS to introduce the speaker.
Hello everyone. It is my great pleasure to introduce my esteemed colleague Professor Sukanta Bose, who comes to us today from Washington State University. Sukant has... Sukant's research interest spans a variety of areas. He has done a lot of work in various aspects of gravitational wave astronomy, the physics of neutron stars, and general relativity. He is a key member of LIGO scientific collaboration, and he made fundamental contributions to both the discovery and our understanding of gravitational waves over the last few decades. His work especially highlights the intricate physics of neutron stars, which are some of the most extreme laboratories that the universe has to offer us. So without further ado, I would invite Professor Sukant to give his lecture today under the Kaapi with Curiosity series. Actually,
You can give them a minute.
Thank you. Thank you. Laser doesn't show, right?
That's an LED screen.
Yeah, I know. So, okay, I'll use the cursor. And this,
Slide.
I believe I'm audible, right? Okay. Figuring out my boundary conditions. Thank you so much to Dr. Guru Prasad as well as Dr. Prayush Kumar for this invitation. It's wonderful to be here. I was just explaining to both of them that I grew up in Bangalore, so every time I get an opportunity to visit, I grab it. So allow accessories, I guess, allow, all right. Yeah, so today I'm going to talk about neutron stars. But before that, let me have a quick poll. How many of you have heard of the collision of neutron stars that made news about 8 years ago? Okay, if you have not heard about it, please don't be shy, it's okay. Excellent. So I keep getting prompts. Keyboard setup assistant, connect or not? Wait.
Not get connected.
Continue. I think that's fine. We'll be okay. All right. So, yeah. So as I just indicated, our story or foray into understanding these highly compact objects will begin about 8 years ago with a collision of two neutron stars that we thankfully were able to detect with observatories on Earth. This was the first time such a collision was observed in gravitational waves. So this is an animation produced by one of my friends and NASA. This person happens to be somebody called Luciano Rezzola, who is a director at the University of Frankfurt. So what you just saw was a numerical animation of two very compact objects, each roughly the size of Bangalore, okay, but very dense. Each one of them has the mass that's a little over the mass of the sun. All of that mass compressed into a size of Bangalore. I know, I just have been through the traffic of Bangalore. You must be wondering, what else can get more congested? So yeah, trust me, this is much more congested. So you're good. You notice that there is a lot of debris that is produced just before the two objects merge into forming a central, more massive neutron star or a black hole right at the center there. This debris is rich in heavy nuclei because neutron stars themselves are made of, as you can guess, neutrons, right? So we'll understand these. We saw a gravitational wave signal from this object, but also electromagnetic signal, and they together were messengers across a band of information. So we learned a lot about them. So what can we possibly learn from maybe this talk? We'll find out whether indeed neutron stars are dead stars, and if they are actually made up of neutrons. Is it just neutrons, or do you also have additional stuff, right? You may be curious, and so I'll try to answer most of these questions. And if they are indeed made up of neutrons, where else do you know neutrons exist? If you say, yeah, I mean, I'm made of neutrons, you're somewhat right. Our body does have loads of neutrons, but they usually, well, not usually, they always come packed in nuclei, right? And these nuclei are parts of atoms, and we are basically made of atoms and molecules that encase neutrons and protons, and also electrons going around those atomic nuclei. But if you're talking about just stripping away the electrons and leaving behind all of the neutrons and then packing them as dense as you can make, then you would presumably get something that is as dense as a nucleus, right? How dense is it? I can give you a number, I can throw out a number, but it may or may not make much sense. Basically, it is about 1 billion times, 1 million times the density of water. We are mostly water, so perhaps you get a sense, right? Billion times million. 1 million is 1 followed by 6 zeros, 1 billion is 1 followed by 9 zeros. So it's extremely dense. If you were to try to take a spoonful of matter scooped out of a neutron star, if you could, then that will weigh billions of tons, right? So, but how does it get to be like that? We'll talk about it. And neutrons, being denizens of atoms, you would expect should obey not the same laws that govern our traffic here, but laws of the microscopic world, the atoms or subatomic particles like electrons, protons. So, and that's the domain of quantum mechanics. Now, if you're already worried that, well, quantum mechanics is so exotic, will I really fathom what it entails for neutron stars? Bear with me, I think you will get some idea about it by the time we are done. So, we'll understand what role quantum mechanics plays in ensuring that neutron stars-like objects exist. In fact, if there was no quantum mechanics, maybe all of it will collapse to a black hole, which is basically nothingness. Okay? So thanks to quantum mechanics, neutron stars exist. Remember that. So now if you're compressing all of the matter of the sun to the size of Bangalore, how dense, we talked about density, but how much of an acceleration will it impose on other particles around it? In other words, how strong will the gravity and the surface of this star be? And the point is, it's going to be extremely large. We'll talk about the numbers in a moment. And that's because it follows Newton's law, roughly speaking. There are corrections to it. But with Newton's law, that if you don't change the mass, but you reduce the distance, then the Newtonian gravitational force goes like 1 over the distance squared. So distance is in the denominator. Smaller distance makes the force larger. So you can guess that, oh, this object should be much more, will have a stronger gravitational force at the surface than our sun. But that can actually produce very interesting physical phenomena, which is why this actually is the remnant of a neutron star. You can see such, and yes, there is some false color here, but if you were to take a telescope and look at this nebula, it will look very impressive. And this debris field was produced by the explosion of the star, which left behind a remnant, which is actually the neutron star. That's a tiny dot there. So if the gravity is strong, then we just heard that, yeah, quantum mechanics prevents this gravitational collapse, otherwise it would be a black hole. But can such objects teach us about the universe at bigger scales? So that's basically the palette we are starting with today. But then, because I already alluded to the fact that these are remnants of stars, let's look at stellar evolution. How does a typical star evolve during the course of its life? Do we know of any star around us? Very good, the sun, I'll take it. How long has it lived so far, ever since it was formed? I'm happy to hear the word billion. You're in the right ballpark. So it's lived for a little less than 5 billion years. Okay, so if you're worried that, oh, that's too old, thankfully it's going to live for another 5 billion years. So you're safe. Your kids are safe, your generations are safe. But if you start with a sun-like star, or actually even somewhat heavier, all the way to about 8 times the mass of sun, or in fact somewhat even lighter, about 80% the mass of sun, all of these stars will basically meet the same fate. Namely, eventually, I'm going to skip through a few details, but eventually it will puff up into what we call a red giant, which will be bigger in size, somewhat less of a surface temperature. But then when it is puffed up, the outer layers are less gravitationally attracted to the center. So they're prone to be lost through what are known as stellar winds, or in this case, solar wind. Solar winds are just streaming particles made of like protons or light nuclei like helium and their isotopes, right? So those solar wind particles will strip the outer layers away, and at the end, so much so that this outer layers can, by the way, expand to cover a distance that could be as far as the current orbit of Earth. Okay, our sun in 5 more billion years can actually expand to that kind of a size, and the outer layers can keep expanding to form or leave behind what we call a planetary nebula. It has nothing to do with planets. Okay, so it's a misnomer in sense, but basically what it is saying is that this nebula of gas and some dust is basically gravitationally bound to the central object, which is now the exposed core of our star. Okay, the exposed core of our star, which is basically rich in the case, helium or maybe lighter nuclei like carbon, oxygen, nitrogen, not much heavier than that. That is what we call a white dwarf. Its size is roughly the size of the Earth. But you're talking about an object, a white dwarf, which is the size of the Earth but much denser. It's about 1 million times as dense as water. Okay, sun's density is roughly somewhat more than the density of water. Okay. Now, white dwarfs, we talked about the size of Earth, but they will have a lot of mass because the density is so high. The mass is going to be still a big fraction of the mass of the sun. Remember, the sun did lose some maybe 20-30% of its mass in forming this planetary nebula. But why is this planetary nebula often very nicely visible? We'll talk about it in a moment. The core is what we are interested in, and that is the white dwarf. It is supported by quantum mechanics. We'll talk about it more. Eventually, this is like dying embers, and when that heat escapes as light, it leaves behind something which is not visible anymore. That's just a black dwarf. Basically the same object which is not luminous. But if the original mass of the star was greater than 8 times the mass of sun, then there are 2 possibilities. One of them is, well, in both cases, it will puff up to become a red supergiant. which will then explode as a supernova. And then if the original mass of the star was between 8 to about 30 times the mass of Sun, its core won't be that big, and it will leave behind the so-called neutron star, which is our main actor for the talk. If the original star were more massive than about 30 times the mass of the Sun, then the core is too dense and cannot hold on to the gravitational, to its own self-gravity, which means that gravity is only attractive, so it will collapse to form a black hole. And yes, we have seen all these three kinds of objects, okay? Now, starting with the Planetary Nebula, this is, in fact, again, there is some false color here, but it is a real nebula. It's called the Helix Nebula, and there is a white dwarf at the center. Not this, I think it's one of these spots. There are some foreground stars. The white dwarf at the center is actually known and has been observed. It is so iridescent because of ultraviolet light that is escaping from those cooling down white dwarf. Okay, and that ultraviolet light, which we are protected from, by the way, sun also emits ultraviolet light, but because of the ozone layer, we are protected or shielded from most of it. Right? We still wear sunscreen because some of it can get through. That ultraviolet light can ionize. The reason it is dangerous to us is because, again, we don't want our skin to get ionized, right? So it ionizes this gas here, which means it strips off electrons from those atoms. And those electrons, when they recombine, falling back to various energy states, some of the light that is emitted in the process is in the visible band. So we can actually see these things in the visible band with telescopes. Okay, now to summarize with white dwarfs, I already mentioned that they're typically the size of Earth, and a sun-like star will shrink to something like this. How big is the sun? You can fit, I think, something like over 100 Earths across the diameter of the sun. Okay, so that is how much we are shrinking it. Of course, the volume goes like a cube. That is how the density grows 1,000,000 times. So 100 times 100 cubed is 1,000,000. Now, have we seen other white dwarfs apart from the Helix Nebula? Yeah. A very well-known white dwarf is, in fact, the companion of the brightest star in the sky. Which is the brightest star in the sky? It's a planetarium. I know many of you know the answer. Sirius, the dog star, which is a bit south of Orion, the hunter, right? Orion is a winter constellation, so soon enough, yeah, you'll be seeing it more and more prominently in the sky. We're approaching winter. So it is in the constellation of Canis Major, the dog, the big dog, right? So the dog is close to the hunter. Of course, these tales were woven by the ancient seafarers because it helped them to remember the relative positions of these stars, right? Because they were used as guides in their seafaring journeys. So this is that star, Sirius. This is actually Sirius A. But Sirius A has a binary companion, which you may or may not have known. And that's that companion. That actually is a white dwarf. This is a picture from the Hubble Space Telescope. Okay? And they have, I think, used some filters to dim the light from the brighter star, which is still evolving. And this is a dead remnant of a companion, which is less bright. In X-rays, which one of these is Sirius A? The lower one or the upper one? The orientation actually has not changed much. So this is the white dwarf. In X-ray, it appears brighter because it emits more X-rays than the actual star that is more luminous in the visible. Okay, so that same star that we call the dog star or Sirius actually is that X-ray point. Anyway, this companion, Sirius B, is a white dwarf, and now let us actually start to unravel the quantum mechanics behind this object. Why did it not collapse under its gravity? It's much more dense than the sun, right? It could, except for the fact that the electrons in such a dense solid no longer remain pinned to their respective atoms. It is energetically favorable for these electrons to mix together and form a sea. Okay, so basically it's more like a state of a plasma. There are ions which are the remnants of the atoms. In this case, again, helium, carbon, depending on the nature of the previous main sequence star. And the electrons form a sea, and this sea of electrons actually exerts a quantum pressure, which was first taken seriously by whom? Sorry, I asked too many questions. By Chandrasekhar, right? And I believe most of you have heard of him. Subramaniam Chandrasekhar, roughly around the time a little later, that he proposed this idea that, you know what, once a star stops or doesn't have enough pressure in the core to be able to fuse light nuclei to form heavier nuclei, because that is thermonuclear fusion. That is how any star burns. Even our sun is currently actually fusing hydrogen nuclei, the lightest nuclei in the universe, to heavier isotopes, principally helium, alpha particle. So, but Subramaniam Chandrasekhar, when he was like 20 years old, so almost 100 years ago, 1930 is the time I'm talking about. In 1930, on his voyage to the UK, he thought that once a star in its core is not able to fuse light nuclei to form heavier nuclei, what could it do, right? There is no thermal support present anymore. Because right now the sun is not collapsing because there is thermal support from the radiation that is being produced in its core, right? But if there is no such support, what is the only force left to the star, to the core of the star? Gravity. Gravity couples to everything. Although we don't feel it, we are all coupled here, okay? So gravity is only attractive. So you would imagine that left to itself, this white dwarf core should just collapse under its own gravity. What is it that keeps it from collapsing? What is it that supports it against that collapse? And quantum mechanics was relatively new at that time. And so Chandrasekhar felt that, okay, could there be something, because classically he couldn't find any reason, right? And that's when he figured that maybe there is quantum mechanics that can come to the rescue. But what are those laws? These laws were known from about a century ago, and that is what Chandrasekhar was also mulling in his head. That one of the things he knew was the Heisenberg uncertainty principle. Again, these names may be a mouthful, but don't worry about it. The basic idea, and yes, they are somewhat counterintuitive because we don't see quantum mechanics playing out in front of our eye on a daily basis, right? But these are laws that still are borne out by observations like those of neutron stars. So the idea is that in the uncertainty principle, what people were finding, physicists, that if you localize a particle like an electron so that its position is known very accurately, then you will have no control on what you will measure for its momentum. Okay? Its momentum can be very large or small. The moment of uncertainty will be large. On the other hand, if you, so that's the situation here. Here, this is the wave nature of the particle, which again is another implication of quantum mechanics, which says that electrons or even photons, light particles, can sometimes reveal their particle nature and other times their wave nature. Electrons are known to be particles most of the time, but we use their wave nature in electron microscopy to form images, right, of tissue and so on. So if you and this wave packet is showing something like an electron which has been localized into a smaller region. But if you do that, its momentum is uncertain. And the way to understand is that the momentum of a wave can be determined from its wavelength. Wavelength is basically the separation between the consecutive crests, okay, of a wave. This wave packet can be formed by superposing many waves of various wavelengths, which basically means that the wavelength of this packet is very uncertain, and therefore the momentum is uncertain. So if you localize in space delta x well, then its momentum is uncertain. On the other hand, if you do not localize it, if you do not localize the wave, so here there is no bound you can see of this wave packet. It's a traveling wave or even a standing wave. But the wavelength is very precisely defined, so its momentum is very precisely measured, right? So delta p here is the uncertainty in momentum, delta x is the uncertainty in its position, and the product in quantum mechanics would say is bounded from below by Planck constant, which is a very small number. But essentially, because this is an inverse relation, it means that if delta P is large, that is the uncertainty in momentum is large, like here, then its position will be well localized, or vice versa. Now, what does it do to that electron gas in a white dwarf? What it means is that if you have removed the thermal support, the star has now become denser, and therefore you have squeezed the electrons into a smaller volume. And that means that you're reducing their positional uncertainty. Yet their delta X is now more precisely measured, is small. If their delta X is small, then because this is the Planck constant, this is constant, delta P has to be large. Delta P is the uncertainty in momentum. But if uncertainty in momentum is large, remember, from Newton's second law of motion, change of momentum is force, and force per unit area is pressure. So if momentum is large, momentum uncertainty is large, the force is large, the pressure is large, and that is the pressure that is able to hold or arrest the further gravitational collapse of the white dwarf. Okay? So that's the idea here, and this is shown in more detail. Like in this case, this wave is localized well in position, but to form this wave mathematically, those of you like doing that, one can show that you can create such a wave structure by superposing multiple monochromatic waves of various wavelengths. So which one of these wavelengths will you choose to describe this? That becomes uncertain. And so this uncertainty principle actually gives rise to a pressure. So these electrons, their momentum is very uncertain, so the force imparted is large, and that is what is one of the factors involved in stabilizing the white dwarf. That's not the only one. The other one, again a consequence of quantum mechanics, is the Pauli exclusion principle. Okay? What does this say? This says that you cannot put two of the same fermions, like electrons or neutrons, in the same state in a quantum system. And electrons come in, spin, two kinds of spin. So their spin direction can be up, like clockwise, or down, anti-clockwise, okay, like this. I should do it with the same hand. But in a white dwarf, because you're reducing the space available to these electrons, they tend to therefore start occupying the lowest energy levels, but while obeying the exclusion principle, meaning in any energy, these horizontal lines are energy states or energy levels. And in each energy level, you cannot have more than two electrons. One of them is spin up and the other is spin down, right? And this basically means that no matter how much pressure you impart, you cannot put more electrons in lower states. They have to rise up in states, meaning eventually the highest momentum the electrons can have, which is related to this energy level, will be large. And if that momentum is large, the consequent pressure is large, and that also contributes to stabilizing your white dwarf. Okay? A similar kind of idea works for neutron stars also, because neutrons are also Fermi particles or fermions like electrons. They obey the same two laws of quantum mechanics. The only difference is that neutrons have much more mass than electrons. Okay? So, as I was saying, in stellar evolution, I just discussed how we produce white dwarf. We already discussed a bit about how neutron stars are left behind by mid-range massive stars. But then exactly what is the mechanism that produces this neutron star, right? Now, there you may have heard of supernova explosions. You it has been a while since we had a supernova explosion in our neighborhood. If you're wishing for one, if you're lucky, you may get it. Because Betelgeuse, again, refers to the hunter, right? One of the stars in that constellation of Orion is Betelgeuse. And it is already, we can actually image its surface. Our technology has advanced that much. And we can see fluctuations in its luminosity, which is consistent with the possibility that it's going to go up or blow up as a supernova any day. Any day means tomorrow or in 1,000 years, something like that. Okay? So we are hoping that it happens soon because, as Dr. Perez said, I am interested in gravitational waves. And one of the things we have not seen in gravitational waves is a supernova explosion. So it will be wonderful to be able to catch it. But what actually happens, right, in a supernova? This is going to repeat itself, but okay, we start with a star right here, but that's like Betelgeuse, where it is about to turn off its ignition mechanism, right? It's at a phase where the core will stop burning, and then the gravity is going to make the core denser, right? In fact, but the outer layers by that time have not realized that the core is actually contracting. Remember, the size of the core is like for white dwarfs, of the size of the Earth and so on. A sun-like star is much more bigger. Betelgeuse is even bigger, but the core is relatively small, and once the core loses thermal support, it's going to contract. But information takes time, right? Because it takes at least the speed of light. In fact, in this case, the speed of sound in the stellar material to be able to communicate to the outer layers, the atmosphere of the star, that, you know what, the core saying that I don't have any support, so you better react. But it takes some time for that information to reach that outer layers. And so by the time the outer layer knows it, that there is no ground beneath my feet and collapses, the core actually bounces back. I mean, it contracts up to an extent, but then the neutron pressure, just like the electron pressure, starts kicking in. So the core bounces, the core is re-expanding, and the outer layer is falling in, and that is what calls for a great collision, right? That's exactly what's happening there. So I'm going to demonstrate that with this. And so as they say in the sea world, okay, the nearest zone is danger zone. Anybody can get splashed with water or hit by the ball. No, I'll take care. So this is not the core. This is a piece of the core. Okay, the core is huge. This is some element in the core, right? And I'll get it to bounce. But when it bounces up, it's like that rebounding core, right? And this is a piece of the outer layers falling, right? And when the two meet, what do you think will happen? Have you seen this? Have you tried this at home? Okay, good. Yeah, but the amazing thing is the momentum transfer. It actually tells you why the debris field is so large and it gets scattered so quickly. So, okay, hold your breath. Maybe one more time. Good. Okay, so that's momentum transfer. So this is basically, basic physics that is happening in a supernova explosion. But what's the evidence for neutron stars, right? I just showed the Crab Nebula and the fact that there is a very dense object here. So how dense? Now we are talking about, again, something like the mass of the sun, maybe 2 times the mass of the sun, but all of it squeezed to the size of not Bangalore. No, sorry, actually, no, I should, to the size of Bangalore, not the size of Earth. White dwarfs are the same kind of mass, but as big as the Earth. But now you take about one solar mass and squeeze it to the size of Bangalore, then you get a neutron star, right? But we actually learned about them first because of the fact that they some of them send a beam of radiation. And the Crab pulsar here does that. There's a pulsar actually which sends pulses of light. And this is how it looks. Okay, so what's happening is some of these neutron stars have a strong magnetic field. And that's not surprising because the sun has a magnetic field. But then if you follow the conservation laws and squeeze the sun to a much smaller volume, the magnetic field will be larger at the surface. And that strong magnetic field at the surface is so strong that it will rip electrons out of the surface, and these free electrons, when they see the magnetic field, they do what electrons even in your lab do when they meet such a situation, okay, an electric or magnetic field. They experience Lorentz force, right? So they get accelerated because of this force, and accelerated particles or charged particles will emit radiation. And in this case, the main beam is along the magnetic axis. But the magnetic axis, let's say the magnetic axis is the blue axis, okay? But this blue axis is not always, not for all neutron stars, aligned with the rotation axis. Okay, the neutron star will be rotating like this in some cases, but by the way, for the Earth, are the two the same, the magnetic axis and the rotation axis? Very good, they're not, right? In fact, Earth's south magnetic pole is somewhat removed from the geographic North Pole, right? The South Magnetic Pole is closer to Canada and not really at the Arctic, unlike the geographic North Pole. So similar situation. So if you have the magnetic axis pointing at you right now like this, you will see a beam of particles there. But if the spin axis is vertical, then this is like a lighthouse, which is going to, so the beam is continuous, except that it comes at you for a flash and then goes away. So that is how we saw it first. We called it pulsars, although it's not pulses that are being sent, right? We are observing them as pulses. And so neutron stars were first established for their existence by looking at pulsars in like 1967. Anyway, so in summary, we just learned that, there are three kinds of remnants for stars. You have white dwarfs. Actually, there is a fourth kind, which like very light stars will not even reach this stage, but that's a separate story. So sun-like stars are somewhat massive stars because of this electron degeneracy force, this quantum force, will not collapse any further. But if you start with somewhat more massive stars, they actually are supported by the neutron degeneracy pressure and in fact some nuclear force also. It's not just the neutron degeneracy pressure. We'll talk about it in a second. But if the original mass of the star is more than 30 times the mass of the sun, then none of these forces is able to halt that gravitational collapse and you form a black hole. Okay? This again is a true image in false color of another neutron star. So and this one is in the small imaginary cloud. So we are finding, actually, among pulsars, we know about 3,000 to 4,000 pulsars in our own galaxy. Okay, although many more exist. It's just that we are not yet aware of them. We keep on looking. Now, in the last part of my talk, I'll focus on what we are learning from neutron stars. So again, a recap, the size is about 11 to 13 kilometers in radius. Density is, as I was saying, a teaspoon would measure several billion tons. The surface temperature can be 10 million Kelvin. The surface temperature of the sun, by comparison, is about 6,000 Kelvin, okay? And the surface gravity, 100 billion times Earth's gravity. So Newtonian laws of gravity fall inadequate to explain everything we see about these objects. For example, the light emitted by a neutron star actually gets redshifted as it climbs the gravitational potential well of that object. And these phenomena are important. I mean, but before I move on, let me quickly summarize also how the interior looks. So the total here is about 11 to 13 kilometers in radius, right? The outer layers are less dense. They are basically ions of iron, nickel mixed with electrons. But then as you go deeper, the ion lattices, they get compressed, right? And so they start dissolving into nuclei. And the electrons and neutrons are still around. But further down, the density reaches about twice rho zero, which is the nuclear saturation density. Basically, rho zero is the density of lead, okay, among the highest densities that you can find on Earth in terrestrial labs. So rho zero is the density of lead, but this can be, in a neutron star, more than twice the density. In fact, by that time, you already have the nuclei dissolve into neutrons and protons. So most of the neutron star is made up of something like 9 kilometers of it is made up of a soup of neutrons and protons. Okay. Mostly neutrons, some protons and electrons. At the center, we don't know. That is why we are making these observations. If they can tell us something about, for example, if you could measure the mass and the size of a neutron star, you can get some idea about how dense the center will be. If it is too dense, like 4, 5, 6 times the density of lead, then here the neutrons and protons will also dissolve into just their constituents, which are quarks. Okay, has such a phase transition been observed? Not yet, but we are finding ways to probe that. Okay, now going to the outside, yes, the fact that neutron stars bend space-time around them is already being used to measure their masses. I was just telling you if you know the mass and radius, right? But how do you measure the mass? For example, if you have 2 neutron stars orbiting their common center of mass, such systems exist and they have been observed. Both are dense, both would curve space-time around them, but because of that, once in a while when the companion comes along your line of sight to the other object, so A and B, right? So you're seeing, let's say, radiation from A, but now it is passing through the vicinity of B because it is in the way, right? Then because of the bending of the space-time around B, the radiation from A actually has to go through that gravitational potential, climb out, and then come to you, which means that the signal will actually get delayed relative to a case where B was not in the way. This is actually theoretically derived and also measured. It's called the Shapiro delay. In fact, this delay can be used to infer the mass of that intervening star. And that is how we know that these are some 1 to 2 times the mass of Sun. The heaviest neutron star so far observed has a mass of maybe a little more than twice the mass of Sun. There are other gravitational effects they can induce. For example, and this is another experiment that is trying to encash on this idea. The idea is, here we just talked about light rays getting delayed or gravitationally redshifted, right? By the way, if you want to understand why this redshifting is happening, there is a loose analogy. It's not completely accurate, but you can think of it as follows. Yeah, you can't see this laser light. Yeah, you need a lot of dust here. So maybe on the road you can see the beam, but imagine you can see the light, right? The speed of light, does it change? No, it is always close to 300,000 kilometers per second. It doesn't change. But if I were to throw a massive object like this, does the speed change before it reaches the top of its trajectory? Right. Its kinetic energy decreases to 0. Why? What happened to energy conservation? It gained in potential energy, right? So, as I said, the analogy is not perfectly accurate, but a similar thing is happening for light. The speed of light cannot change, but some of the total energy of the system has to be conserved. Otherwise, you can build a perpetual machine shooting beams, up and down or throwing particles. So, light gets redshifted as it climbs the gravitational potential of a massive object, because that is how it loses energy. Because the redder the light is, the longer the wavelength, and smaller the energy. Okay, the energy of photons is h times nu. Nu is the frequency. Longer wavelengths have smaller frequencies, smaller energies. So that's one way to understand it. But so this is gravitational redshifting. But here there is another effect. This is called bending of light. How do we use it? The idea is that suppose you have a neutron star that has a hot spot or two. But why hot spot? Why should a neutron star have hot spot? The way they can get a hot spot, meaning a spot on the surface which is more luminous than the rest of the surface. If, for example, they have a companion from which they can steal matter. Okay, they can steal matter from a companion star, and as that plasma falls onto its surface, it can ignite some local, even thermonuclear reactions, becoming a source of radiation. And as this star spins, eventually this spot of light will go behind. So let's say the observer is here. You're observing these neutron stars from the right, looking to the left. Right? So what happens is that if the star is very compact, then this spot, which is now on the other side of the star as viewed by this observer, right? This observer can still see some light from behind the star. Why? That is because of bending of light. There again, we should not be surprised. So we have a gravitating object in the Earth, right? If I throw something, it falls. If I throw with a greater velocity like ISRO does, right? Then also it will fall. But if this is Earth and you throw something with large enough velocity, it can fall so that it actually forms an orbit, right? With light, the same kind of thing is happening here, except that light has a large speed, so you would expect it to escape without any bending. But gravity, if it is strong enough, can bend light. And so that's what's happening here. If this object is very compact, for the same mass, all of that is squeezed into a smaller space, the surface gravity is very strong, and light emitted by this spot here, some of it can get bent because of the gravity and come towards the observer. Of course, there's quite a bit of light that will escape to the other side. Okay? So this light bending can be used, again, to measure the size or the compactness of this object. This is less compact, the same mass, but over a larger radius. Here, this is the invisible zone. You cannot see that spot from, on this side as viewed from this observer. Okay? So this idea is actually being used by an experiment called NICER to be able to understand the properties of neutron stars. So we are using gravity to help these processes. Now, final stretch, in the last 5 minutes, what I'll show is what happens when two neutron stars come close to each other, or a neutron star comes close to a black hole. They start stripping away matter, right? And this is an animation made by my colleague at Washington State, Matt Dewey, and his colleagues. Dr. Ravish Kumar from ICTS also collaborates with the same group in numerical relativity. So here, we are showing a neutron star that is orbiting a black hole. It's in a numerical grid. So that is, this box is keeping track of the fact that the neutron star is tidally getting deformed, just like the moon and Earth also deform somewhat, right? There are tides. But eventually, the neutron star gets torn apart by the black hole. A good bit of the mass falls into the black hole, sometimes even forming jets. But then there is a reasonable fraction of the mass, could be about 10% the original neutron star, which gets strewn out along this orbital plane. And these are decompressed blobs of neutrons, right? These are lots of neutrons, and so they're unstable. You know that even when you try to form artificial nuclei or elements in our lab, it's very difficult. That is because they're unstable to fission. They'll just break apart. You cannot hold them together. Otherwise, they will radioactively decay. That's exactly what's happening in this debris also. These are neutron-rich blobs of matter which are unstable. So they either do fission, break into smaller nuclei, or they radioactively decay, producing photons and neutrinos. And therefore, eventually they can be observed even from Earth. And that is what happened with the first animation I showed you, 1708, 8 years ago. We not only saw gravitational waves, that was a slightly different case. It was two neutron stars actually colliding with each other. But we saw gravitational waves, but we also saw this electromagnetic emission from these radioactive and fission processes. Okay, I've been talking about gravitational waves. That since you have some sense of the gravitational curvature now, space-time curvature, gravitational waves are just ripples in the space-time curvature. And we are observing those waves with detectors like, LIGO-Hanford, which is a couple of hours drive from my institute in Washington State. So I often spend a lot of time here. But the good news is that we are also building a detector in India. This is just an artist's impression, but we are building LIGO India in Aundha, somewhat in eastern Maharashtra. Okay, I was actually associated with LIGO India for about 10 years. And, but in the final couple of slides, I'll wrap up by telling you what are we learning from observing these binaries with gravitational waves and the accompanying radiation, right? One of the things we learned, so here what we are showing is 8 years ago, we saw this frequency versus time map, this track of the gravitational wave signal. This is exactly what we expect, that as these two neutron stars come close to each other, their signal frequency and amplitude will rise before they merge. And the merger happened at this time. The time is on the horizontal axis, so T0 is the time of merger. And about 1.7 seconds later, there were these detectors in Fermi and integral, which picked up excess gamma ray photons, high energy photons. This is exactly what we have been seeing from short duration gamma ray bursts. But we, in the past, were not completely sure that these very energetic explosions or bursts we see in the sky are because of these mergers. This was the smoking gun evidence that they are two are related. Neutron star mergers with other neutron stars or black holes will produce gamma ray bursts of this kind. Okay? And this particular object, as he already implied, was viewed in infrared, near infrared radio. So this is the NGC 463 galaxy. This is the host galaxy, very bright. The central bright object is always that galaxy in these three panels. The neutron star explosion have this binary merger happened at that point. You can actually see a red spot here, perhaps, at least for those of you who are close enough. You can see it here also, but after some time, Actually, no, this radio emission showed up sometime later. Initially, this was missing here. Okay, so it is good to compare before and after images. That that this radio emission happened as expected after some time had elapsed from the merger. It wasn't present initially. Can you learn something more about the universe using neutron stars? And the idea is yes. But what could it be? One thing we know about the universe is that it is expanding, right? Did we all hear that news? What was the news? Not that it is expanding, but two different teams of scientists are tussling each other, not agreeing on the value of that expansion rate. Okay, there are two ways of measuring this expansion, one of which Hubble himself followed again about a century ago. He was looking at faraway galaxies. Even actually at that time they were relatively nearby, like Andromeda and somewhat farther out. And he noticed that these galaxies are, regardless of where you look, in whichever direction, they are all receding from us, as long as they're far enough, not too close. Because if they're too close, then just like Andromeda is in fact coming towards Milky Way because they're gravitationally interacting. Okay, so you have to go beyond the gravity of our galaxy to be sure that the behavior is not because of our gravity, but because maybe of cosmic expansion. And he established that the speed at which these galaxies are receding from us is proportional to their distance. Okay, so V is proportional to distance. This is a constant of proportionality, which is that expansion rate. Okay, so this is the rate at which the universe is expanding. It's like the raisin bread. Okay, this is a bread in an oven with these dots being the raisins or galaxies, and just like when you break the bread, it expands, it puffs up, and the distances between these raisins will increase, right? The same thing is happening here, and what you need to do is measure the redshift of the faraway galaxy, because the redshift tells us how fast it is moving away from you. But you need a way to measure the distance, and that is often tough. How do you measure the distance? Thankfully, with these neutron star mergers I was talking about, gravitational waves actually carry information about the distance. And if you can tell that, oh, this merger, the gravitational waves from here came from this galaxy, then the spectrum of this galaxy will tell us how fast it is moving away from us, how much the redshifted the light is from this object. So those are the ideas we used to try to resolve this fight. Okay, well, not quite a fight, but this is the tussle I was talking about. There is this green team that measures the expansion rate by looking at the cosmic microwave background radiation, which I didn't have the time to go into. It's a technical detail, but there is one way of measuring that tells you that the speed is something like somewhat less than 70 kilometers per second, okay, at every million parsecs, or 3 million light years. Every time you go about a distance of 3 million light years away, the universe relative to you will be expanding at something like 70 kilometers per second per megaparsec. They measure it to be something like 68 kilometers per second, whereas this orange team, which looks at nearby stars to which the distance can be measured, they find that value to be something like 73, 74 kilometers per second. But both measurements have error bars. The tussle is that these error bars don't overlap, which means they are quite sanguine that, my measurement is not overlapping with your measurement. So somebody has to be wrong. If you're looking for a research project, this could be it. Okay? Chances are if you resolve it, you'll get a PhD, but maybe even a Nobel Prize. Seriously. So that's what we are trying. And this 17017, because we saw the redshift of its galaxy and the distance in its gravitational waves, we found this kind of this blue curve gives the probability of the value. But there is a problem. As you can see that this spread in the probability is large, which means that we are not taking sides. Right now we are very democratic, very neutral, right? We are not telling that, the green team is right or the orange team. We are subsuming both. That's political. But with more observations, the hope is that this blue curve will thin down, and when it thins down, maybe it will be more like the green or more like the orange, or maybe something different. Either in any of those ways, the hope is we'll learn something new and it will be useful. Okay, I'm almost out of time, so I'm going to actually rush. I was going to say the Nobel Prize this year was given for quantum tunneling. And if you're curious, but quantum tunneling in macroscopic objects, like a collection of billion electrons, is almost like a classical object. But we actually saw that tunneling through a barrier, okay, which you don't expect classical tennis balls to do, but wave can do. So those guys actually found macroscopic collections of electrons to tunnel through a barrier. And in neutron stars also tunneling happens, if you're curious. And that's because when I was saying that here, these nuclei dissolve into just neutron-proton fluid, it is happening because from the nuclei, the neutrons actually tunnel away into the surrounding space. So the tunneling phenomena is is present in a big object, otherwise classical object like a neutron star. What holds for the future? This is a zoo of the many binary black holes and some neutron stars that gravitational wave detectors like LIGO and Virgo have found. In the future, we don't have to go into the details here, but this is like the extent of the visible universe. And the hope is future detectors like Cosmic Explorer, Einstein Telescope in another 10, 15 years, we'll be able to see every neutron star merger or black hole collision that happens in the universe. In other words, if you're seeking to maybe build a career out of such observations, you'll be busy, okay, which is a good thing. So to recap, yeah, neutron stars are, I hope I've been able to communicate at least some sense of why they're like nature's quantum experiments, right, playing out at a large scale, stellar scale. The G2 17017 observations by LIGO and other neutron star observations by NICER have shown us that nuclear force actually adds to the neutron degeneracy force to be able to make the neutron star somewhat bigger and less collapsed. Okay, without the nuclear force, that wouldn't be possible. And then neutron stars warp space-time around them, and this actually has tested Einstein's theory. That's the other thing. So far, Einstein, even a century later, he's still passing all the tests. He has not failed a single one. But we'll keep trying to prove him wrong, because that is what science is, right? And finally, neutron stars are like the standard candles. In the last part, I was talking about the cosmic expansion, because they can be used in their distance, combined with the redshift, can be used to measure the expansion of the universe. Thank you so much for your time. I hope we have some.
Thank you so much, Professor. So we'll have a question answer session now. Please raise your hands. You'll get a mic. Please ask your question in the mic.
Yes, a nice presentation. Thank you. How far are the neutron stars?
Good question. How far are they? I really didn't give an. Yeah. So 17017. That was at a distance of 40 million parsec, where 1 parsec is about 3.26 light years. So if you do the conversion, it is about 120-ish light years away from us. In comparison, Andromeda galaxy is about 2.4 million light years away. So these are quite far out, but still not at cosmological distances. If you want to see more of them, then it is better to have detectors that can see at least about 10 times farther. Okay. Advanced LIGO will not quite reach that kind of a horizon, but Cosmic Explorer will reach way beyond that. But yes, about 100, so over 100 million light years. Yeah. Now, I also mentioned that they are related to short duration gamma ray bursts, where we don't see gravitational waves because they're too far. But we know there are also neutrons, collisions involving neutron stars. Those we see up to close to a gigaparsec. So that's over 1 billion light years. So these objects, yes, they're colliding deep in the universe. All they need are detectors that they're able to, sense them. Yeah.
So one more question. Human brain has a limitation the way it thinks. We think in a particular fashion, logical, analytical, like that. But the design of the universe looks very different. Whatever we perceive, is it reliable? How much it is reliable?
Yeah, that's an excellent question. Thank you for asking it. It's beyond my talk, but it's an important question. It goes into the heart of what the scientific method is. Like, there are so many things that are written in the scriptures also, right? And I get asked, how do you know that physics has already seen everything? Could be, it's quite possible that this particular statement is true. You guys have not realized it. Fine. But see, we follow a method known as the scientific method, which has to do with that, okay, make some observations, then try to explain those observations, like, whether the Earth is at the center of the solar system or the sun, right? That's the question. We have to make observations to be able to rule one of those possibilities out. So that entails model building, formulating hypothesis, but that explain that observation, but also posit new predictions. Einstein did the same thing. Okay, you have to make new predictions from this model or hypothesis that can be tested. Making hypotheses that cannot be tested is not science, right? So now, to more directly answer your question, we are limited by the type of observations we can make and the type of models we can build with the mathematics or physics we know, right? It is quite possible that new phenomena arise as new observations are made and new methods of analyzing them become available, right? So, and similarly, old theories can get debunked. By Newtonian gravity, we know is still pretty good for launching satellites. But the satellites still face an effect when it comes to keeping time, which Newtonian gravity cannot actually, doesn't predict, which is what Einsteinian corrections, would actually take into account, which is how the global positioning system works, right? That is because clocks closer to the surface of the Earth tick slowly compared to those farther away, right? So what I'm, in conclusion, it's basically like a game of chess, right? This is something Feynman had said. Suppose you come into a game of chess, which two players are playing, right? And you know nothing about chess. You're just seeing that, okay, somebody's moving the pawn this way. And as you're seeing those movements, you're formulating your own laws. This is how science works. We are formulating our laws. But then you see the queen also keeps moving seemingly like the pawn. But then it makes a sudden jump. And then you realize, oh no, this queen actually behaves differently than a pawn. Until that jump, that observation happened, you thought they behave the same way. Science is like that.
Thank you, sir. Presentation. It was wonderful. Yeah, here I am. So I have notes, but I will keep it to just one or two. So at one point you said that neutron star is hot to touch. Now we know that the reason we find the heat from a sun is because of fusion. But
because of fusion.
Fusion, right? But in neutron star, where is that heat coming from? It's obviously right. There's only neutrons.
No. It is the heat that is trapped in the star. This core was hot, right, when it was producing the thermonuclear energy. Now, new energy source is no longer existing, but it is a heat capacity. It has retained that heat, and it's now more or less like a black body that is losing that energy through these photons at various energy scales. So it is the heat that was in it during the burning process that has been retained, which is gradually dissipating.
Just one follow. What happens when it loses all the heat? What happens when neutron star?
Yeah, so there could well be a number of stars that are already in that phase that exist, but we don't know about them because they're not emitting luminous enough radiation. They're too faint. Right. So fractional stars, neutron stars, may be exactly like that.
Okay. Thank you. Just one more question. When you were explaining like why dwarfs won't collapse because of Pauli's exclusion principle or uncertainty. But when we talk about giant stars and neutrons, then definitely it collapses to it. But does it somehow violate any of these principles when it collapses?
Oh, the formation of the neutron star? Yeah, thanks again. So I didn't get into that much. But if the original core is really very massive, and it stops burning because perhaps it already has something like iron or nickel in it, and those are elements that have a nuclei that have the highest binding energy per nucleon, right? At that stage, if you try to fuse them, it's not an exothermic reaction. You will not produce any more heat. So that is when that thermal support is lost, right? That is when the star starts collapsing under its gravity, and when that collapse happens, the electrons, you would expect, will start, just like in a white dwarf, will try to resist through the electron density pressure. but that pressure is not enough to arrest the collapse. So the collapse proceeds further, and then the electrons, the most energetically favorable process that's available to the electrons at that stage is to get absorbed into neutrons. No, into protons. Sorry, the electrons and protons combine to form neutrons, which is why it's then predominantly a neutron star.
Correct.
Right? And then it's at that time the fermion available to the star is basically the neutrons, the sea of neutrons, and then the neutron degeneracy pressure kicks in, right? And depending on the original mass, even the neutron degeneracy pressure is sometimes not enough, and that is when you have to go to the nuclear interaction, the strong force, where at very close distances nucleons actually repel. And that combined with the neutron degeneracy pressure is able to finally arrest the star. If that too cannot arrest, then it will become a black hole.
No more question, but just one clarification. When we are saying about, when you're saying gravitational lensing that we see in the and measuring distance, is it the same?
Yeah, it's self-lensing. Here, typically when we talk about lens, there is an emitter, and there is another object which is a massive object, or the lens, which is bending light from the emitter to the observer. But here, the neutron star itself is the lens, and the spot on it is the emitter. And most of the light may be going that way, but some of the photons can bend and actually travel in the other direction.
Thank you, sir.
Yeah. Yes.
Thank you very much for the insightful presentation. My question was, could you elaborate on the potential barrier experienced by the neutrons in the neutron stars to encounter quantum tunneling?
Yeah. So I'll pick up where I left off. If you bring the neutrons too close to each other, then they experience repulsion. And if you want the details, this has to do with exchange of what is called the vector meson. Okay, that's another particle. But that's at the size of a neutron or a proton is about 10 to the negative 15 meters, about a femtometer. But we are talking about bringing them closer than that, like a quarter of a femtometer, right? But if they're slightly away, maybe because they're not packed that tightly, then the force is attractive. Okay, and that is because that force is due to another kind of, meson, a pion. But if, so in that attractive state, you have a potential that well, and that potential well can have different states of bindedness, right? But when the neutrons, when you start packing them, eventually you'll have some neutrons that are in the higher energy levels in that well. And at those higher energy levels, those are the neutrons that are most prone to actually escape the potential, it's a nuclear potential, into the outside of the nucleus. So that is a form of tunneling. So in fact, if you do the detailed calculations, it seems that that phenomenon is very much present, because what we are seeing so far is really consistent with mostly neutrons that have actually tunneled out of a nucleus in a neutron star. What we have not established yet is whether there can be also quarks, where the neutrons themselves are dissolving. Maybe the quarks are tunneling. Okay, but as far as the neutrons tunneling, that has already been established in some sense by our observations. Okay, yeah.
Sir,
Maybe, yeah, we'll take a quick and then we'll go there. Yes.
sir, I have a couple of questions. First one is, you said in the simulation, as the two neutron star approaches each other, it will expand, right? It will spaghettify.
Oh, you mean, okay, no, tidally deform, right?
Yeah, yeah.
Yes.
So it means that delta x will change in the Heisenberg uncertainty principle, and hence how do we know that that two colliding objects is neutron star itself?
Oh no, okay. So yeah, so you have a situation where the two neutron stars have come close to each other, right? And they feel the tidal force, right? The tidal force is going to stretch them out, just like with the Earth-Moon system, right?
Yeah, yeah.
And so yeah, so indeed, you will actually then I don't know whether you have seen pictures of the comet Shoemaker-Levy falling into Jupiter. There also, there was a situation where the comet was tidally stretched and then torn apart. Okay, so you can have a similar situation even in this neutron-rich material, where material gets torn apart into relatively smaller blobs. So yes, they are decompressed, and you're not even talking about neutrons that are degenerate anymore. True. Okay, and they are unstable to decay. So in that sense, it is no longer in the same state as they were when they were in stable neutron stars.
One more question.
Okay.
There is a theory that at the core of the neutron star, we can find a strange particle, a strange quark. Is there any possibility that we can detect other quantum particles from neutron star collisions?
Yeah, it's very much possible. All it will take is each one of us in the whole country to give up a coffee or give that money to the LIGO India project so that it can build a more sensitive detector. But no, more directly, more sensitive gravitational wave detectors can actually answer this question. We are already trying it as follows. If there are, so I already mentioned that the core of a neutron star can be 5-6 times more dense than the lead nuclei. At those densities, in stable conditions, we have no experiments on Earth that can tell us about the nature of the nuclear force. That's a very important message from here. In colliders on Earth, you can reach larger densities, yes, but those are ephemeral. They're very transient. They're not going to probe stable matter, but they're also teaching us about nuclear physics. Anyway, but at those high densities, several times the nuclear saturation density in the core of a star, yes, neutrons may actually, as I was saying, dissolve into quarks, but could there be certain types of quarks which are somewhat heavier than the up or down quark, like strange quark is what you're talking about. There are particles like hyperons that are made up of strange quarks. Can they exist, right? Can there be a phase transition in the nucleus or in the deep core of a neutron star to produce that kind of a phase? And the answer is, if that happens, then the macroscopic properties of the star will change. That's the good news. Like a quark star, for the same mass, will be more compact. And like with the lensing, etc., we're talking about how we can measure how compact a neutron star is. If we find stars, neutron-like stars, which are more compact than we have ever seen, chances are that that's because it's predominantly made of quarks, perhaps even of the strange kind. Now, different quarks have additional different properties. Like with strange quarks, you can the material can be more viscous. Okay, so that has a different kind of physical effect, which I can't go into the details of here. But we have done some research about this regarding how it can be probed. Okay, if you want to hear, just because of viscosity, larger viscosity, there can be more tidal heating. Tidal heating is a phenomenon that happens even in Io, the moon of Jupiter, right, which is very volcanic. That's because of the tidal interaction with Jupiter as well as other Galilean moons like Europa and Ganymede, right? So these things can be probed, and we are looking for such signatures in our observations. I think there was somebody here, and then we can come back, I guess.
Yeah, I'm a data scientist at Reliance Jio. Last year, there was a lecture, Nobel laureates lecture in Chennai, where I realized that maybe it's fundamental physics, but most of it are statistical data science studies, clustering. That's how they find stars only. So a lot of AI is involved here. How post ChatGPT and LLMs has your work accelerated? And I'm sure that even for applied research, the amount of budget is so less. I'm in that, and fundamental research, the length of success is so huge that the amount of money goes into it is very less. Would AI make you guys more productive? And what are the other ways we are trying to ensure that we can push science further?
Yeah, no, that's again beyond my paycheck for this talk, but it's a good question, so I'll answer it to the extent I can. Using artificial intelligence or ChatGPT like tools to do science, right? The first thing is espouse it, embrace it as much as you can, but in a careful way. We'll be fools if we don't encash on any such technological advance. It can be very useful in teaching. A part of me feels if I had something like that, my learning as a student would have been accelerated way beyond what I actually did. Okay. You have to know how to ask the right kind of probing questions to extract the most. But there are also limitations at the moment, which may be overcome in the future, perhaps in 5-10 years, which is that ChatGPT is still, or LLMs or other AI tools are not good at certain kinds of ways of synthesizing new knowledge from existing. They're very good at scouring for what information exists and then forming a scenario consistent with that. They can do some problem solving though. Okay, of course they can solve certain kinds of integral differential equations and so on. They can extrapolate from statistical data taken earlier to what can be predicted in the future with different degrees of probability. You should use those tools, but the best, I think, option we have, see, we cannot, it's safe to assume that, resisting it will be futile. So then the best thing you can do is learn how to adapt. The humans have been good at adapting, but of course, every time there has been a technological, paradigm shift like this, adaptation, I guess, has become more challenging. It has taken longer time. There have been tidal distortions, socioeconomic and whatnot. I'm not a socioeconomic theorist, so I wouldn't go there. But I think at the moment, you can still use to improve the quality of your work, and you should do it. Not in my field. In some other fields, maybe, but I cannot hazard a guess there. Oh, okay. No, they've accelerated research of certain kind, like pattern recognition. So yeah, it's context dependent. What you're asking, if you have, which we do in gravitational wave data, right? There are signals of certain kinds, but oftentimes we are confounded by lots of noise artifacts, just terrestrial disturbances. And if you are doing it, but humanly, it is not possible to do an accurate job scouring the data, reams and reams of, terabytes of data per day, right? But neural networks can do that. ResNet, confound net, transform networks, they can actually do a much better job of classifying these features. So we are using them, but typically they are, so they're helping research, yes. But I wouldn't, maybe that is semantic. I perhaps will not call them fundamental research, which is where I was going. Yeah. Yes.
Hello. So mine is a little layman's question, a little Harry Potter mode, so don't mind if it doesn't make sense,
Sure.
but I'll take my chance. You mentioned that neutron stars bend space-time, and you also shared this phenomena of hotspot, where matter is stolen from a particle, and this results in the bending of light. Can you, and because you mentioned neutron stars are sirens for our understanding our own cosmos, can you give us, can you talk a little more about this warping space-time, and if there are any observable phenomena within our cosmos or even right here on Earth? I don't know if that's even pragmatic, but this idea of daylight savings or this idea of tidal impact on gravitational weight of objects, anything like that, I'd like to know.
That was my whole talk.
Oh my God.
No, I'll start. Okay, I'll maybe answer some of it. Like, what exactly does it mean, bending space-time, right? So imagine that this whole room, that you're at a rock star, concert, right? With some laser show. So you have a coordinate grid that is set up with laser beams, right? So laser beams going this way, that way, in all three, orthogonal directions, right? What Einstein showed, even though he didn't have lasers then, right? That if a dollop of mass or energy or inertia, if it came by, it's actually going to bend this grid of light. And that's what's called warpage, right? And he interpreted that as curving space-time, that the effect of the gravity of this mass that you suddenly introduced actually curves space-time, and you can see that curvature through the bending of light. Okay, now, how would you see it with real material objects like pen and paper? This is again an analogy. What you can do is that you can say, okay, yeah, space is three-dimensional. Let's just take a section of it. Okay, so there are laser lights here. So I just take a sheaf out of it, and that's the sheaf. But if I now bring in a mass like the sun, okay, what does it mean that it bends the, the laser beams or therefore space itself? So this is a two-dimensional spatial slice. What it means is that to curve it, I can either, crumple it and it will look terrible. I'll do a hopefully neater job. I'll just do a tear. So, because that also is a leading order, correction to flat space. Okay. So the introduction of the sun, so that's my sun. Okay. The introduction of the sun basically curves the space. So this is basically, to first approximation, a curved slice of three-dimensional space. Okay. And now if you ask that, okay, why did Einstein do this? That is because Einstein already knew that astronomers are grappling with this question that, Mercury's orbit is not a closed ellipse. Kepler wanted it and Newton's laws are consistent with that. So rather it's a precessing ellipse. Okay, very slight precession, but cannot be neglected and cannot be explained by perturbations of other solar system objects. So closed ellipse, but because of the curvature of space-time induced by the sun, it no longer remains closed, and it falls within itself and precesses. So this was, again, coming back to the scientific method. This is not the full scientific method. This is Einstein coming up with a hypothesis that explains a known observation, which is that Mercury's orbit seems weird. You may ask, what about the other planets? They also do it to a much smaller extent. Mercury does it most because it is deep within Sun's gravitational potential, because it is the closest planet, right, to the Sun. The scientific method requires that you now take this theory or hypothesis and make a new prediction. Einstein did that too in 1915. He said, if this is true, then light rays should also bend. Of course, I started my analogy with laser because but Einstein didn't have that benefit, right? Einstein said this curved thing will also bend light. And you can see that because, okay, otherwise, suppose there are two parallel rays of light, which, and the sun doesn't exist. So there are, two stars far away. You on Earth see these parallel lights, parallel rays of light. But because of sun, this, and the space-time gets curved, and you see light rays get bent, right? So this was the prediction, which was verified later in 1919, and that is when Einstein became a household name. But so that's then completing the scientific method, which is very essential. Otherwise, you can just explain anything and get away with it. That was a part of your question, but yeah.
So we'll take one question from the YouTube live stream. Somebody has asked, how fast does a neutron star rotate or spin?
That's a good question. Neutron stars can rotate, in theory, quite fast. Among known neutron stars, we have some of the milliseconds pulsars. Okay, let me just give you a number. So basically, it can rotate as fast as something like hundreds of cycles per second. Okay. Beyond that, there is a problem because it has to shed angular momentum. It's a material object, unlike a black hole, which can, perhaps for the same mass, spin somewhat faster, right? But the Crab pulsar that I was talking about, for example, spins at a rate of something like 30 cycles per second, right? Yeah, 30 hertz, yeah. Yeah.
In the light of the gentleman's question, second question especially, when it comes to the structure of the universe or the way in which it works at the cosmological level, or even if we go to quantum mechanics level, our everyday senses tell something different, in fact. See, quantum tunneling from our day-to-day point of view, it is very difficult to appreciate. See, the gravity was interpreted in one way by Newton and in another way by Einstein. Is there any universal reality as far as the structure and the working of the universe is concerned?
Yeah.
This is more philosophical than...
No. What we do know is that Einstein's theory of gravity also has solutions which are problematic, like it has singularities. So, and we also, if you believe in quantum mechanics, as you were saying, then we have been successful in understanding the quantum nature of every other fundamental force. starting with the electromagnetic force, and then the weak nuclear force, which I didn't talk about much, but in the strong nuclear force. Then why not gravity? Gravity is also conceived as another fundamental force, but we have not succeeded in quantizing it. So there are indications that, well, something has to give, but that's a good thing. It means that my students will be employed, that I can give them problems that they can scratch their head on. The way I perceive science is that, but this is something, it's cliched now. The more we learn, the more we dig, the more questions also come up. So,
Thank you very much. Just as the professor was telling, there is an announcement. As far as the bending of light, that aspect is concerned, we are going to arrange a documentary jointly with Raman Research Institute next month. We are trying to do that. Kindly see our website, and whoever gives us cell phone numbers, we'll try to send through WhatsApp the information. That's a very good documentary made by a Canadian. It's about an hour of 1 hour documentary.
and thank you very much for the wonderful outreach work that your planetarium is doing.
Thank you very much.
Okay.
Thank you, sir. First of all, amazing lecture. My name is Anupray. I create content on space through my platform Cosmonomics. So one interesting thing I wanted to ask about the neutron star. You mentioned you used the metaphor like siren, beacon, and all, right? Like even lighthouse. Is there I read somewhere an article about using neutron star or pulsar as navigation or like cosmic GPS. So I wanted to know, like, is there been some work done on that front? And is that possible, or is that still in the realm of science fiction right now to use the neutron star as a navigation?
No, we actually did something concrete with it. You're talking about specifically, can we use pulsars as space markers, like landmarks, right? And the answer is that in the Pioneer spacecraft, right, there were plaques that were that they carried, that we made, and we communicated in those plaques information in the form of just bits, okay, Boolean bits, 1 and 0s. We communicated our, what are the lightest elements and our DNA, very interestingly. But one of the things there was the location of the solar system. If this Pioneer spacecraft eventually lands up on another stellar system, right, how will they know where it came from? How would you tell it, right? The idea they devised, and it may have been because of Carl Sagan, but I'm not completely sure, is that tell them the position of the sun by pointing out where some of these, relatively nearby powerful pulsars are. Because each of these pulsars has its own characteristic pulsing period. And presumably an intelligent civilization will know about them and will use them as guide marks to triangulate or whatever and find where the location of Earth is. Thank you.
Thank you all. Thank you for attending this talk. And we have coffee and snacks outside. Please have it before you go. Thank you again.
Thanks.